Okay, so we were discussing the other day, if you remember, that we defined work as the force, and we could actually look at it as network, and net force through a given distance, cosine theta. Okay. Now remember, this is when the force is constant. Okay. When we have a constant force. All right. And so if we look at pushing an object, just say a box, here's X initial, here is X final, or S initial, S final. And so we apply a constant force. Force applied is constant. All right, we should get here then, we'll eventually reach X final, come to there. And when we look at the graph of this, we should have a nice straight line. Okay. All right. Let's see, what was last week's lab? Last week's lab was friction. Yeah, okay. All right. However, that is not always going to be the case. All right. As you well know, most of the time in nature, things don't always move at constant rates. Some do, some don't. Like gravity, we know gravity's constant for a given location. So if I apply force then, I'm just going to put this mass on here to kind of help give me a little resistance here so I don't shove it off the end. Okay, so if I apply a force, if I apply a constant force, then I should get a nice straight line graph. However, if I come back and I push and then I slow down, then I push and slow down and push and slow down, okay, speed it up and slow it down, speed it up and slow it down. That's a non-constant force. And you know if you graph that using your motion sensor, you're going to get something like that right there, okay? And so how in the world do we find the work done from x1 to x2? Because that's not a linear function, okay? Absolutely, okay? It's pretty obvious, isn't it? So if we look then at this, notice that you can break this down into sections. Okay, you could actually break it down into sections and do the area of those rectangles. Okay, you could do that. But in actuality, what we end up doing is, of course, an integration, as Scott said. Okay, because what is an integral? Well, it's the area under the curve, right? It's the area of something. Okay, in this case, we're looking at what? The force applied through a given distance, right? Force versus distance. Now, you know, other times when we look at some of our quantities in electromagnetism, you'll see that it'll be a little different. Okay, when we look at electricity, when we look at voltage, so the quantity, what the quantity is, doesn't matter. Okay, so we're looking at an integral, and notice it's the final position, just like from the initial position. Just like when you do an integration, you have your upper and your lower limits, okay? So we're looking at the force applied through a given distance, and the force is non-constant, or we can say varying, we can also say non-constant, okay? It's a non-constant force. Now we're going to look at this today in our video analysis. We may be looking at a non-constant force, and again, we may be looking at a constant force. I'll just leave that for you to figure out when we do it. Okay, if it's a constant force, it's just a plain old algebraic, you know, you do the product and boom, we're done. Cosine theta, we're done. If it's a non-constant, a varying force, then we take the integration. And if we graph it, if we can graph it, it's a whole lot easier in Logger Pro. Just do the integral, highlight the area on the curve, boom, hit integral, and we're done. It's a lot easier to do, isn't it? Okay. Of course, if we have a function, you know you're going to take the integration of the force with respect to x. Okay, and so you'll integrate whatever quantity, and I'm pretty sure I gave you some problems on chapter 6 where you had to do an integration or two. Okay, where you have to integrate it. All right, and of course you'll do that integration with whatever part of the function has x in it. That's what you integrate. I mean, you know that. All right, from calculus. Okay. But as far as anything else changing, nothing else changes. The unit's the same. The definition is the same. Okay. It's just that we're doing an integral. Okay. All right. So now here we see, again, if the force is constant, again, this is just re-emphasizing what we've already covered. If it's a constant force, notice you get a nice little rectangle. You take, the length times the width, boom, we're done. Okay. All right. All right. Now let's look at Hooke's law. So we're going to look at three things today. We're going to look at Hooke's law. We're going to look at work done with a varying force or non-constant force. We're going to look at Hooke's law, and then we're going to look at power, okay? And then we'll look at some problems. All right, so Hooke's law basically says that if we take a spring, of course here I have, and we'll do this lab either next week or week after, okay? Well, if we take a spring and it's at equilibrium position, at zero position, x initial, okay? Of course, it's not stretched, is it? However, if I take my hanger and put some mass on here, we see the string begin to stretch, don't we? Right? And so we see the change from the equilibrium position to the final position. There's a change in x. In this case, you could actually put y in here. Just take they did it horizontally. Okay, just tilt it. Same, that doesn't change a thing, okay? Nothing changes. Well, with the except that we have gravity here pulling the weight, but again, we have the restoring force, because you know what happens if I take the weight off, what's going to happen? It's going to go back to equilibrium position, isn't it? And what causes that? Well, that's called the restoring force, okay? That's called the restoring force. So here's, their equation, Hooke's law. Now notice this looks very similar to Newton's second law, doesn't it? Very similar. It looks very similar. It's similar to what? MA, isn't it? It's similar, all right? I didn't say it's exact. The difference is we're looking at displacement as opposed to acceleration, aren't we? But now we know there's a relationship between changing displacement and acceleration, because what is acceleration? The rate of changing velocity. And what is velocity? The rate of changing displacement. So there is a relationship there, okay? Except we're not looking at acceleration per se. We are looking at change in displacement, or how far did it stretch. Now again, you can just change that x to a y. It's not a big hairy deal, okay? It's not a big hairy deal. Our spring constant is going to be newtons per meter. That's called our spring constant, okay? Now, if you take, and we will do this lab, if you take masses and keep hanging them on that spring and then plot the change in displacement versus the weight that you add, which, remember, weight's a force, you're going to get a nice little straight line. Actually, it should be this way. Okay? All right?
Well, if you count the resting position as zero.
As zero, it doesn't matter. Yeah, you can do it either way. I think when we do it, it's going to be the other way, if I recall. But it's still the same, okay? Now, there's one thing they left off here, and I'm a little aggravated the authors did this. They left off the negative. Okay, now this is, by the way, this is Hooke's law. If you didn't get that. That right there is Hooke's law, okay? Now, they just said that that if you stretch a spring a given distance x, and again, we just did it. Here was our resting position. Here's our resting position. Here we stretch it. So this is x initial or x naught, and this is x final, okay? I don't like using naught. I never have. I know the book does, but I don't. I've always used initial and final, because that naught throws people. Like, what's that little zero? Okay. Okay. All right. So if you see, notice it's newtons per meter. There's your force, and so a newtons per meter, and what is a newton per meter? A newton is a kilogram meter per second squared, so there's your mass. Okay. All right. And so the spring constant is newtons per meter. That's called in Hooke's law. And it's a very simple equation, very simple equation. But again, why the negative? They left it off, and it really needs to be there. Why the negative? Is the constant negative? No. The what force? Very good. The restoring force. It's very important you understand that. The reason the negative is there, please get this, okay? It's not because the constant's negative. I can't think of any constants other than gravity that's negative. And the only reason it's negative is because, remember, gravity is downward towards the center of the earth, okay? That's negative other than gravity. So, look, when I stretch a spring out, we know, common sense, y'all. Come on, you don't have to have any science background to know. You've played with springs, you've played with slinkies, that if I stretch it, it's going to go back to its original position, okay? So the negative tells me that when a force is applied, there is something called a restoring force in the opposite direction. And that's the only reason the negative is there, okay? That it's telling us that the force, there's a restoring force opposite, okay? Whether it's horizontally stretched or whether it's vertically stretched, doesn't matter, okay? Does not matter. Position, X, Y, doesn't matter, okay? All right, now, taking Hooke's law, if we integrate it, and basically if you look at this right here, y'all, how did we get this? Well, we get it this way. If we take Hooke's law and integrate it, okay, and this is X final and this is X initial, we wind up with that right there. We wind up with what? Kx squared. Okay? That's all they did, is they just integrated Hooke's law with respect to displacement, okay? Oh, yeah, excuse me, thank you. I knew I was leaving something off. 1/2 x squared, yeah, because when you integrate it, yeah, it's divided by 2. Okay? Thank you. All right? And that's all we did. Real simple integration. Very, very easy. And so, now remember, notice this is work, okay? And of course, what's the units always going to be? The units will always be joules. Okay? All right, so that's our units. Always. Anytime you see work, even when we look at work, electrically speaking, it's still going to be joules. All right? Now, don't confuse work with voltage. It's not the same thing. It's related, but not the same thing. Voltage is the work done on the charge. All right? We often say it's the push behind the charge. And that's a good way to, because if you get into high voltage, and I'm getting a little ahead of myself, that's next semester. You get into high voltage, what would it do? Bam. It'll literally knock you down. I've heard stories of people wiring up, I grew up in construction, and wiring up dryer plugs hot. And they were in a hurry, and they got into that hot wire. And if they got into both of them, it was 240. They only got one of them, is 120. But usually if they're knocked backwards, they got into both of them, 240. And people have literally been knocked on their back from it. And that's good because 120 will make you go into tetanus and kill you if you're not careful. 120 is actually more dangerous than 240. And even higher than that, what's above 240? 480? Yeah, 480 voltage will really rattle your teeth. Of course, any of it can kill you. But these lines out here, I think, coming in is 5,000 volts coming into at the pole. It comes to the pole, I think, 5,000 volts. And it probably steps it down to 480 because of all the units we have. Probably steps it down. But anyway, so a little different. It's work and voltage is not the same thing, but they are related, okay? So we'll talk about that next semester, all right? Look at that next semester. Okay, so there's another equation right there. This is the work done on a spring, okay? Or elastic work, if you want to write it that way, elastic work. Work done on a spring or elastic work. So there's your two equations, Hooke's law and the work done on a spring, okay? Okay, very, very easy. And remember the negative on Hooke's law, okay? So here now, what about energy for along a curved path? Well, really, it doesn't change that much, except instead of it being S, the change in distance, we're looking at the what? We're looking at the angle between the initial position and final position, okay? All right? And so it actually becomes an integral of the what? Of the position Yeah, do what now? Force parallel, yes, absolutely. Force parallel. So that's really all that changes. All that changes is that right there. Not that big a change. All right. Not that big a change. Okay. All right. The L is this. Yes, it's that right there. Yes. Like from, it doesn't matter if you want to pick from here to here. Yeah. 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 Technically, yes. Okay. Okay. All right, and then power is really easy. Thank God we're getting into some easy stuff. How do we define it? Rate at which work is done. There's your good definition. Notice that if we want to know average power, we just do the change in work divided by the change in time. However, if we want to know instantaneous, that right there ought to send up a red flag when you hear the word instantaneous. You know what we're going to do. Come on, y'all. You've had it in calculus. I know they've talked about it in calculus. When you hear the word instantaneous, you automatically know we got to have a derivative. Okay? We're going to do a derivative, and yes, it'll be with respect to time. And so we take the derivative of work with respect to time. So we have joules per second, and what do we come up with? We come up with a watt. W-A-T-T, watt, capital W. All right? And so 1 watt of power is the number of joules, or 1 joule per second. Okay? But if you know how much power you use, you're looking at how many joules you used in a given time interval. Okay? All right. Now, they give you and I do want you to write that down, the conversion of horsepowers to watts. Please remember that. Okay? Because horsepower is the English version of power. Okay? It's the standard or English version. All right? Please write that on your note card, on your formula card. All right? That's another one of those conversion factors. Okay? So the rate of changing work with respect to time, or the rate of work with respect to time, is power. This is how we pay for our utility bills. They don't charge us the number of joules. It's a little bit. It's just easier to look at how much joules we used in a time interval. Actually, they charge us by the kilowatt hour. And what is a kilowatt hour? It's 1,000 watts per hour. Okay, the number of watts per hour, 1,000 watts per hour. So they look at kilowatt hours instead of watts, kilowatts. And that's how they charge. They like charge different companies like 29 cents, 18 cents. I don't know what does Alabama Power charge. Anybody know? It's higher than TVA. It's probably what? 22 cents a kilowatt hour, something like that. TVA, I think 17 or 18. I'm not sure. They're cheaper. TVA is cheaper than anybody, probably in the United States. And I'm not dissing Alabama Power. I'm just saying it's just a fact. Okay. It's actually called a Southern Company now. I think they don't go by Alabama Power anymore. I think it's a Southern Company. I think they bought out Georgia Power and Alabama Power, and I think Florida Power. Who else? Gulf Power, yeah. Yeah, they bought out a bunch of power companies now. It's just called Southern Power or something like that. Southern Company, yeah. Southern Company, yeah. Okay. Okay? And that's how you get charged. When we buy hair dryers, when we buy a dryer, we buy a washing machine, we buy an electric hot water heater, you look at the little yellow sticker on the side. It'll give you everything in watts. Okay? Again, why do we look at it in watts? We want to know how many joules in a time interval we're going to use. It's easier that way than to look at the number of joules we used. Okay. All right. Okay. And that's power. Real simple. Real simple. Okay. And again, this is showing you. This is just walking us through this. Now, another way we can calculate power. Here we look at instantaneous power. Another way to calculate it is looking at the force times the velocity of the particle. Okay? Force times velocity of the particle. So if we look at this, we've got what? Force is what? Newtons times what? Meters per second. And what is a Newton meter? A Newton meter is a joule per second, which is a what? A watt. Okay? So there's actually two ways we can look at it, how much force through a given velocity is applied, force times velocity. Like we apply a force to this cart and it moves with a velocity of 1 meter. We apply a 1 Newton force at 1 meter per second velocity, then we'd have what? We'd have a power of 1 watt. Okay? So we don't have to have work. We can actually do it with force and velocity. Okay? So there's your two equations for power. You've got work divided by the time or force times velocity. Okay? All right? Never have figured that picture out. I guess the car stalled out, I guess. So they had to go back the old way and get the horse to pull the car. That'd be the luck, wouldn't it? Okay. All right. Any questions?
How do they get horsepower? I mean, I get that it's supposed to be how much fully force the horse has, but how did they figure that out?
I don't know. That's a good question. I've never researched that, why they came up. Well, I do know it's if you have one horse, that's equivalent to 1 horsepower. You got 2 horses, it's equivalent to 2 horsepower, and so forth. But again, you have to look at you're talking about the comparison to watts. Is that what you're talking about, or are you just talking about horsepower in general?
I'm wondering why they even call it horsepower. Like, how did they figure out that a horse has that much power behind it?
Well, I would assume it would be, if you look at it, just the amount of mechanical work that it can do. You follow me? Yeah, how much it can push or pull, yeah. Mm-hmm.
How did they figure that out?
Well, yeah. Yeah.
It started off with this for like, to open this.
Yeah. It takes 2 horses or 3 or whatever, yeah. Mm-hmm.
Pull this carriage.
Yeah. And the gateways or the dock or the whatever it is weighs, 10,000 pounds and yeah.
Eventually
Okay.
established.
Yeah, establish this quantity, yeah. And of course, they relate it back to watts and joules by doing what? Well, looking at the mechanical equivalent of work. Okay? You say, well, how do they get it to a joule from a horsepower from a joule to a watt? Well, they just compare it back. Remember what James Prescott Joule did with when he discovered that there was a mechanical equivalent of work. Okay? And you can take any situation in which energy is produced. Like, for example, how do they know in a chemistry lab? How do they know if you're, for example, you're going to build a car battery? Okay, well, all that's chemical. All right, but how do they know how much power it will put out? Well, the mechanical equivalent of work. Okay, they know the joules per mole of energy produced when you mix the chemicals with the lead battery, and so then they just go from there and convert it over to mechanical work. Okay. All right. So you can do it from chemical to mechanical or mechanical back to chemical. Okay. You can do it either way. All right. And we'll do a lab next semester where we will look at the electrical equivalent of heat. It's a really neat lab. It's a very simple one. It's got like it's got a voltmeter. You have a voltmeter or you have a voltage source, and then you have a little cup with a light bulb in it and a thermometer. But we get real close. It's really cool how you can prove the electrical equivalent of heat. Instead of the mechanical, you can actually do it electrically speaking. Okay. If you ever wondered how they know, how much heat a light bulb will put out or how much energy a wire coiled in a little heater will put out. Okay. Well, there they look at the electrical equivalent of heat instead of the mechanical. Okay. It's pretty neat. I've wanted to do the mechanical one, but it's pretty involved. I have to have liquid nitrogen. Yeah, and I've always wanted to do that one. We might try it next semester. My electrical one's easy and simple and don't cost a lot of money. We have to go buy liquid nitrogen. That's not too expensive, but it doesn't last long. Even in the little viewer flask, it might last 2 months, and you spend $50 or $60. So anyway, and I hate to get it for one experiment, but we might. I don't know. We might do it. We'll be doing Boyle's and Charles's Law, and I always like to play around with liquid nitrogen when we do that. Okay. All right, and that's it. Okay. All right, we still got a lot of time. Let's look at some problems because I know y'all are itching to get to those. Let me stop the video and start a new one.